In the middle years of the 20th century, as the railway industry was consolidating and reorganizing, as the economics of railway operation were becoming increasingly important to every company's survival, as managers and engineers looked at their own fleet operations and saw the complexity and the cost of maintaining dozens of different types of locomotives, there emerged a particular kind of engineering ambition that took hold of the minds of railway designers and railway managers across the industry. The ambition was the dream of the universal locomotive, a machine that would be capable of handling every kind of service that railways needed to perform. A locomotive that would be powerful enough for the heaviest freight service, fast enough for the fastest passenger trains, efficient enough to reduce operating costs compared to specialized machines, flexible enough to adapt to the radically different operating conditions presented by different routes and different services, and economical enough that owning and operating one universal locomotive would eliminate the need to own and operate many specialized locomotives designed for specific purposes. The dream was rational, grounded in clear economic logic. If such a universal locomotive could be built and could perform adequately in all services, the economics of railway operation would be transformed. Railways could dramatically reduce the number of different types of locomotives they had to maintain in their fleets. Workers and mechanics could be trained on a single type of machine rather than on dozens of specialized designs, with all the associated training costs and the slow accumulation of expertise that each specialized type required. Parts inventory could be simplified and rationalized. Maintenance facilities could be consolidated. The infrastructure required to support locomotive operations could be dramatically reduced. The operating cost per unit of work performed could be reduced because the locomotive would be optimized for general efficiency rather than specialized for expensive peak performance in a specific service category. The vision was powerful enough that it captured the imagination of designers and managers at multiple railways. If one company could solve the universal locomotive problem, the competitive advantage would be substantial. If one company's engineers could design a machine that other railways recognized as superior, that could operate all services adequately, that could reduce costs across the entire fleet, then that company would have developed a technology that other railways would want to purchase or emulate. The universal locomotive was not just an engineering challenge. It was a business opportunity, a chance to develop a machine that could transform not just one company's operations, but the entire industry. The locomotive that represents the most complete attempt to realize this dream was built in the late 1950s by a team of engineers who believed they had found the engineering solution to the universal locomotive problem. The locomotive was designed with meticulous attention to creating a machine that could do everything that railways needed a locomotive to do. The designers conducted extensive analysis of different railroad operations. They studied the power requirements for heavy freight service. They analyzed the speed requirements for passenger service. They examined the efficiency characteristics that different services demanded. They built mathematical models. They conducted tests. They attempted to find an optimal compromise point where the locomotive would be adequate at all tasks without being so compromised that it was inadequate at any task. The locomotive that emerged from this design process had adequate power for freight service, adequate speed for passenger service, adequate efficiency to keep fuel consumption reasonable and operating costs competitive, adequate flexibility to handle the variety of operating conditions that different routes presented. The locomotive was not designed to be the most powerful freight locomotive that could be built. It was not designed to be the fastest passenger locomotive that steam technology could achieve, but it was designed to be good enough at both services to make the operation of specialized locomotives unnecessary, to be economical enough that the savings in fleet management and training and parts inventory would offset any performance compromises that the generalization required. The company that had funded the design and development of the universal locomotive had invested heavily in the engineering effort. Multiple design teams had competed to produce the best solution. The company had conducted field trials and operational studies. The company had surveyed railway operations across multiple railroads to understand what combination of characteristics would be most valuable. The company had consulted with railroad managers and engineers to understand what capabilities would make a universal locomotive attractive to potential customers. The company was convinced, at the end of this process, that the universal locomotive represented the future of railway operation, that other railways would see the advantages and would order similar machines, that the universal locomotive would eventually become the standard equipment across the industry, just as diesel locomotives had become the standard freight and passenger power after the post-war transition. When the universal locomotive entered service, it performed adequately. The machine was capable. The locomotive hauled freight trains and passenger trains. The locomotive maintained schedules on passenger services. The locomotive hauled full-sized freight consists on freight routes. The locomotive did not fail dramatically or reveal fundamental design flaws that would have justified abandoning the universal locomotive concept. By every objective measure, the universal locomotive was a successful machine that accomplished what it had been designed to accomplish. Separate from any ideological commitments to universalization, the locomotive simply worked. But what happened over the years of service revealed something important about the difference between theoretical engineering and practical railway operation. Something about the way that specialized solutions sometimes outperform general solutions, even when the general solution is carefully designed and well engineered by skilled designers working with the best available tools and methodologies. The universal locomotive was good at everything, but it was not best at anything. The freight locomotives that specialized in hauling heavy trains at low speed could haul heavier trains than the universal locomotive. They could start and move trains that the universal locomotive could barely move. They could maintain speed on steep grades that would have required helpers if the universal locomotive was assigned. The passenger locomotives that specialized in hauling lighter trains at high speed could operate at higher speeds with greater efficiency than the universal locomotive. They could maintain schedules that the universal locomotive could not match without straining the equipment. The universal locomotive could do both, could haul freight and could haul passengers, and could operate at reasonable speeds, but it did not excel at either. When a railroad manager needed to haul a heavy coal train, the universal locomotive was adequate but not ideal. When the same manager needed to haul a fast passenger train, the universal locomotive was adequate but not ideal. The specialized locomotives excelled at their specific tasks in ways that the universal locomotive, being optimized for generality, could not match. The consequence was that the universal locomotive did not replace the specialized locomotives as its designers had hoped, and as the company that had invested in its development had anticipated. Instead, the universal locomotive coexisted with the specialized machines. The universal locomotive was used for services where a universal solution was appropriate, where the combination of capabilities that the universal locomotive offered was adequate, even if not optimal. But the universal locomotive was not suitable for the services where specialized capabilities were most valuable, where maximizing freight capacity or maximizing speed was the operational priority. The railway company that had invested in the universal locomotive found itself operating the universal machine alongside a fleet of specialized locomotives that continued to be necessary for the services where specialized performance was important. The dream that had driven the development of the universal locomotive, the vision that a well-designed general machine could eliminate the need for specialized machines, collided with operational reality. Operational reality turned out to be more complex than the engineering analysis had accounted for. Operational reality included economics, but it also included the specific requirements of different services, the operational preferences of different regions of the company, the existing capital investments in specialized infrastructure and specialized maintenance expertise. The company could not simply replace its entire fleet with universal locomotives. The company had to continue operating specialized locomotives because there were specific services where specialized locomotives performed better. The universal locomotive that had been designed to eliminate the need for other locomotives instead became simply another type of locomotive, one option among many, used for services where its combination of capabilities was adequate, even if not optimal for any specific service. The dream of the universal solution had collided with the reality of railway operations, and the reality had won. The universal locomotive persisted, continued to be used, served its assigned purposes, but never achieved the revolutionary impact that its designers had hoped for. The vision of transforming the entire railway industry through universal standardization never came to pass. What happened to the universal locomotive over the subsequent decades reveals something important about how technological solutions interact with the systems they are designed for, about the unexpected complexity that emerges in real operating systems compared to the assumptions built into the original design. The locomotive itself was well engineered. The machine was mechanically sound. The locomotive performed its assigned duties reliably. It did not break down unexpectedly. It did not require extraordinary maintenance. But the machine had been designed to solve a problem that turned out to be more complicated than its designers understood. The problem was not simply that railways needed more efficient equipment. The problem was that railways operated a multitude of different services, each with different requirements and different constraints. And while a universal solution might be theoretically elegant, practically speaking, it was not operationally superior to specialized solutions when the specialized solutions were well designed and when the benefits of specialization outweighed the costs of fleet complexity. The universal locomotive was eventually scrapped like most steam locomotives, as the diesel transition eliminated steam from active service. But before it was scrapped, before the end came, the universal locomotive had demonstrated through decades of service something important about the limits of universal solutions, about the enduring value of specialization. The machine had shown that it was often better to have several good specialized machines, each optimized for specific tasks, than to have one universal machine that was adequate at everything but excellent at nothing. One machine that did not require extensive crew training in multiple specializations, but that also never delivered the performance that specialized designs could achieve. The significance of the universal locomotive lies not in what it accomplished, but in what its lack of revolutionary impact revealed about the relationship between engineering design and operational reality. The universal locomotive was designed based on sound engineering principles. The analysis that supported the design was thorough. The machine that resulted from the design was well built. The cost estimates were carefully calculated. The efficiency projections were based on rigorous engineering analysis. But the universal locomotive failed to accomplish what it was designed to accomplish, not because it was poorly engineered, but because the fundamental assumption that railways wanted a universal solution turned out to be incomplete. What railways actually wanted was solutions that were appropriate for their specific needs. Specialized solutions that had been optimized for specific services and specific operating conditions were more valuable than general solutions that attempted to serve all purposes equally. The engineers who designed the universal locomotive were not wrong in their technical analysis. The engineers correctly understood that a machine designed to be adequate at everything could perform all the functions that railways needed performed. But the engineers did not fully account for the value of specialization, for the way that focusing on a specific set of requirements could allow designers to optimize in ways that general designs could not match, for the cumulative advantage that specialized solutions delivered when an entire fleet was considered, rather than when individual machines were evaluated in isolation. The engineers had designed the machine as if the optimal solution would be to maximize performance across all services equally. But operational reality suggested that it was better to maximize performance in specific services and accept reduced performance in other services, rather than to compromise everywhere. The universal locomotive stands now as a monument to the limits of universalization, to the attempt to create a single solution for multiple problems, and to discover that the single solution, while capable of addressing all the problems, is not optimal for addressing any of them. The machine was not a failure in the sense that it failed to accomplish what it was asked to do on a day-to-day basis. The universal locomotive successfully hauled trains. It successfully moved cargo and passengers. It successfully performed the functions that were assigned to it. The universal locomotive was a failure only in the sense that it failed to accomplish what it was supposed to accomplish, which was to make specialized locomotives unnecessary and to revolutionize how railways thought about equipment and fleet management. What the universal locomotive reveals is something about the nature of technological ambition and the gap that can emerge between what engineers believe they can accomplish through careful design and what actually emerges when the designed solution encounters the complex realities of an operating system. The universal locomotive was designed by people who understood railway engineering thoroughly. The machine was designed with the best knowledge and tools available in the 1950s. Engineers applied sophisticated analysis techniques. They tested their assumptions. They consulted with experienced railway operators. But the designers could not fully predict how the machine would perform in the context of actual railway operations, how it would interact with the existing fleet, how railway managers and operators would make choices about where to use it, and where to reserve specialized machines for specialized services. The universal locomotive became, in the end, simply one locomotive among many, distinguished primarily by the fact that it had been designed with such ambitious and transformative goals and had failed to achieve those goals. The machine persisted, performed its functions reliably, was used as a general-purpose locomotive when specialized capabilities were not required. But the dream of a universal locomotive that would transform railway operations, that would eliminate the need for specialized machines, that would simplify fleet management and reduce costs across the entire industry, remained a dream that was never realized. Other railways, observing the experience of the company that had invested so heavily in the universal locomotive, chose not to invest in similar experiments. The universal locomotive remained a singular case, a lonely monument to an ambitious vision that had not survived contact with operational reality. And when the universal locomotive was eventually scrapped, when the machine was cut up for metal like the vast majority of steam locomotives, what remained was the knowledge that even well-designed, well-engineered machines sometimes fail to accomplish what they were designed to accomplish, not because of technical failure, but because the fundamental assumptions that shaped the design turned out to be incomplete or incorrect. The universal locomotive teaches a lesson about the limits of universal solutions, about the value of specialization, about the complex relationship between what engineers can design and what operating systems actually need, about the way that theoretical elegance can collide with practical reality, and how practical reality often wins.